Hello everyone. Okay, so we are looking at topic 4.5. We're on page 15 in our packet. And I want to show you, we taught it last year in Gen Chem and Honors Chem. I can't remember if we did it the year before. But it's called a BCCA table. And it's a different way of doing stoichiometry. And if we don't know if we're dealing with a limited or an excess reactant, then it can be a really useful way of making that determination. Okay, so we're going to use this balanced chemical equation to describe what a BCCA table is, how it should be used, and then how you can identify when you have a limiting or an excess reactant. Okay, so first thing, here's my balanced chemical equation, and I'm actually going to rewrite it so I can kind of spread them out a little bit more. So we have a C3H8 plus coefficient of 5, O2, turns into 3 CO2 plus 4 H2O. Okay. And we're going to take this balanced chemical equation and we're going to put it into this table, okay? Where the B stands for before the reaction occurs. C means that there's going to be a change. The next C is where we're going to calculate. And then we're going to get this like after. Okay. Before, change, calculate, and then after the reaction. So what's going on before this reaction happens? What change is going to happen during the reaction? Then we need to do some calculations based on this change. And then after the reaction, what's it looking like? What do we have left with? And we're going to analyze the BCCA for all the reactants and the products. So for our reactants and our products, okay? Now, unless otherwise stated, we can make this assumption that we're going to start with all reactants and no products. So it's extremely common to start with 0 products. And as I do this, everyone let's write it right here. Only moles when it's a BCCA table. This BCCA table is awesome, but it only works with moles. So any numbers that I'm writing in here, I'm not always going to be writing down the units because it's going to get extremely repetitive, but we're talking moles. Okay. Now, the change, I haven't said what we're starting with. Like, there's not a problem here to say, oh, we're going to start with this many moles of C3H8 or this many moles of O2. I'm going to add one in just a little bit. But the change is based on the coefficients. So we have a coefficient of 1 in front of the C3H8, a coefficient of 5 in front of the O2, a coefficient of 3 in front of carbon dioxide, and then 4 in front of water. So we know that these reactants are going to be turning into products. So whatever amount of reactants I'm starting with, it's going to be decreasing over time because this is turning into these things. So whatever starting amount is going to become less over time. So the reactants always are a minus, okay? And then the products are always a plus because we're going to be making products. And then how much we are gaining and losing is dependent on these coefficients. So since there's a 5 in front of here, this is going to be minus 5x. And since there's a 3 in front of here, this is going to be plus a 3x, and a 4 is plus a 4x. And then when it's 1, then it's just x. Okay? One of these reactants is the limiting reactant and one is the excess reactant. And we don't know how much we have of each. So one's going to be the limiting, one's going to be the excess. We don't know how much that's going to be yet. So let's do that. Let's say that a question tells you that we're going to have, let's do 4 moles. 4 moles of C3H8. That's what we're starting with, okay? And we're going to have a lot more than that. We're going to have, let's just double it, 8 moles of O2. Man, there's a lot of O2, but does that mean that it's the excess reactant? Let's find out. One of these, after the change has occurred, is going to equal 0. So it's like if I start with 4 and I minus x from that, this one might equal 0. Or if I start with 8 and I minus 5x from that, so 8 minus 5x from this one, that one might equal 0. Okay, whichever one actually equals 0, that's going to be our limiting reactant. And the way that we figure out which one's the limiting reactant is we're going to calculate for x on both of these. Okay? And so we have 4 minus x, so I'll just add that to the other side. So 4 is equal to x. Okay? And then over here, I would add the 5x to the other side. So 8 is equal to 5x. Oh my goodness, 5x. And then we would divide by 5. So 8 divided by 5 equals x. 8 divided by 5, 1.6. Okay, listen carefully. The smaller x value is the true x value. This is what x equals. X does not equal 4. X equals 1.6. So then this one does not equal 0. This one does equal 0. The limiting reactant is the one with the smaller x value when you set them both, when you set all the reactants equal to 0. And once we figure out what the x value is, we can plug it in here. We're going to plug it in here and here as well. Okay? So we truly end up with 0 moles of O2 at the end of this. This is the limiting. But now I'm going to take the x and I'm going to plug it in right here. So like 4 minus 1.6, because that's what x is. So we're going to end with 2.4. So we get 2.4 moles of C3H8. That's what's left over. That's the excess. Okay? And then here, we're take what you started with, which is going to be 0, and then it's going to be plus 3x. Like, this is the calculation that we're going to be doing. Okay? And this is going to be 0 plus 4x. And we know that x is equal to 1.6, so it's going to be 3 times by 1.6. Okay? So that equals 4.8. So we end with 4.8 moles after this reaction, and then 4 times by 1.6 equals 6.4 moles. So this is the amount of moles we end with. So we get a lot of really important information here. By using a BCCA table, we found out that O2 was our limiting, and that when the reaction is all done, that we're going to end with 2.4 moles of C3H8, we're going to have 4.8 moles of CO2, and then we're going to have 6.4 moles of H2O. Okay? And if we are not in moles in the beginning, we need to convert to moles using a one-step goalpost. And if we need our answers to not be moles in the end, then we take the final answer and we convert it to grams or whatever it is it's asking of us. So let's practice this. I apologize. First off, the example number 2 and number 3, I can't believe I didn't catch this. They're identical. Okay, so number 2 and number 3 are exactly the same. So we're just going to use this entire page to figure out and answer this question. And it's telling us, and this one's a little more clear, so it's telling us when a student adds 30 milliliters of 1 molar hydrochloric acid, HCl, to 0.6 grams of powdered iron, a reaction occurs according to the equation above. When the reaction is complete at 273 Kelvin and 1 atmosphere, which of the following is true? And when I look at my answers, I'm seeing remaining amount of moles. I'm talking about excess amounts, and it's talking about how much is being produced. And so really what we should do is a BCCA table and plug the amount of moles in to see what we're ending with, which one's the excess and how much is being produced. So I know I'm going to need to go from this 30 milliliters of 1 molar HCl. I'm going to figure out how many moles this is. And same with the 0.56 grams of iron, I need to figure out how many moles, because that's what can go inside my BCCA table. So I'm going to use this space up here. So concentration is moles over volume, or volume times by concentration equals moles. And it said that the volume was 30 milliliters, so 0.030 liters, times by the concentration, which was 1 molarity. And so then that's just going to equal 0.030 moles of the HCl. Okay, great. I know how many moles of HCl. Now I need to do a goalpost to figure out moles of iron. So we have 0.56 grams of iron. And then I have my periodic table here. It's 55.85 grams per mole of iron. Okay, plug this in my calculator. .0100027 moles. Okay, now it's important I keep these long numbers. I may shorten it inside of my BCCA table, but I'm storing the long numbers in my calculator so I can go back and grab those, because we don't want to round until we get to the very end. Okay, so let's build this table. So we had iron plus 2 HCl turns into iron chloride and H2. Okay, beautiful. BCCA. Alrighty. Iron. Great. Now, before this reaction happens, we just calculated it up above. There's 0.010027 moles of iron. There's 0.030 moles of HCl. We have 0 of our products. We haven't made any products yet. Okay. Now the change, there's a coefficient of 1, so this is going to be a minus x, this is going to be a minus 2x, my products. This is going to be plus x and plus x. Okay? Now, we're going to be taking this 0.01, etc., this long number, minus x, and we're going to see if that one's equal to 0. And then we're going to do 0.030 minus 2x and set that one equal to 0. Okay. And these ones we know in a moment we're going to be doing 0 plus x and figuring out what that's equal to, and a 0 plus x, so we'll end up with the same amount of moles for both of those. So let's calculate. This one's easy. I'm just going to add x to the other side. So we have 0.010027. That's what equals x. And then I'm going to add my 2x to the other side. So 0.030 equals 2x. And then I'll divide that by 2. So 0.03 divided by 2. And we get 0.015 is equal to x. Okay. So a 0.015 or a 0.010, oh, this is the smaller x value. That is my true x value. Like x actually equals that. It does not equal this, okay? The smaller x value is the true x value. So if you were to plug this back in, then this does equal 0. Iron is our limiting reactant, and HCl is our excess reactant. Because that's exactly what we're going to do. We're now going to take X and we're going to plug it in right here, and we're going to plug it in here and plug it in there. Okay? So if we take 0.030 minus 2 times by what we know is X. Okay. So 0.03 minus 2 times by what X is. And see how I'm grabbing the long numbers? Can you see my calculator okay? Alright. So then we end with 0.009946 moles of HCl. And then 0 plus X is just going to equal X, right? 0 plus X is just going to equal X. 0 is equal to X. And we know X is 0.010027. I haven't even touched or talked about sig figs. I'm not rounding until the very end of the problem. And so let's see what it says. Answer option A, HCl is in excess. Oh, it is in excess. And 0.100 moles remain. Okay. Oh, not quite. And then we have HCl is in excess, which is true. 0.02 moles remains unreacted. Nope. This is how much we had. Make sure I'm not missing something up above. 0.03, nope, we're good. Okay. 0.015 moles of iron chloride has been produced. 0.01, not 15, okay? So let's now check on our last option here. And so we know how much H2 has been produced. Like we know the amount of moles of H2 is 0.010027 moles. Okay. And then it tells us the temperature, 273 Kelvin. We know the pressure is 1 atmosphere. Our R value, I'm doing PV equals nRT right now, just heads up. Our R value is 0.08206. Atmospheres. Oh, sorry. Liter atmospheres per mole Kelvin. Mole Kelvin. And we're going to solve for volume. Okay. PV equals nRT. And then we're solving for volume, so I'll divide by the pressure. nRT divided by P. All right, let's see. Moles times by R, 0.08206, times by temperature, 273, divided by the pressure, which was 1 atmosphere. Okay, nice. And so we get 0.2246 liters, and then look at that. Part answer D, 0.22 liters of H2. Now, something I want to point out to you. We didn't have to do the PV equals nRT, because we did eliminate all the other answer options. Like we did say that HCl is excess, but we did not produce 0.1 moles. We produced 0.009 or 0.01 moles. That's why I was a little hesitant. I was like, ooh, did we like get a mistype there? And then we had HCl is excess. Yes, it is, but we did not produce 0.02 moles. And then we did not produce 0.015 moles of this. So by knowing that all of those were wrong, we can assume that the answer is D, and then if we have time, we can check using PV equals nRT. Okay? So this is kind of like one of those culminating stoichiometry questions. It doesn't get any more difficult than this. This is hard as it would be, but this is a great example of showing you how we can use that BCCA table, add everything in that we need to. And this, like, there were so many different items that went into this. We had to figure out how many moles based on concentration and moles based on grams. We put that in our BCCA table, and then we took info from that BCCA table and used PV equals nRT to get a final answer. So much chemistry knowledge that went into just that one question. Okay. We have time that I want us to do one more. Okay, so I'm going to give you an example. So we're going to skip we're on the next page, page 17. We're going to skip number 4, and I'm looking at number 5. And with number 5, it only gives us one reactant, and it says what the excess is. And if this is the case, if you don't have to identify which one's the excess reactant and you're just working with the limited reactant, then you can still use a BCCA table. Like, that will still get you there in the end. But you don't have to. You could just use a long goalpost. That's another option. Either one is fine, but let me show you. So, what mass of water? So we want to end with grams of H2O. Is produced when we have this many grams of methane that is burned, okay? And it was telling us earlier, let me double check. Make sure I get this, tell you the right one. Methane. You're not expected to memorize it. Yeah, that's what I thought. You're not expected to memorize what methane is. They would tell you in the prompt that it is CH4. Okay. Alrighty, so we're starting with that many grams of methane, and then we've got excess not carbon dioxide, excess oxygen. Okay. Alrighty, so if this is the excess, it doesn't limit our reaction, so I don't need to worry about the excess. And we do need a balanced chemical equation to see what's happening, though, and it's going to be burnt in oxygen. So we're going to be taking CH4. It didn't clarify if it is a solid, liquid, or a gas. And we are going to be reacting with excess O2 gas, and then it's going to turn into water, H2O, and then there's something else here, and it's CO2, and this is a chemical reaction I'm going to need you guys to know. It's a combustion reaction. More specifically, it's a hydrocarbon combustion, and we've talked about this before. So if there's a molecule that contains only hydrogen and carbon, it's nonpolar. There's lots of things, but also when it combusts, when it reacts with O2 every single time, it will produce water and CO2. Okay. And then we're going to balance this equation. So I have 1 carbon, I have 4 hydrogens, and on this side of the reaction, there's 2 oxygen right here. Ooh, I might sneeze. Excuse me. So I have 2 oxygens right here, and then I have another 2 oxygens right here. So a total of 4 oxygens over here. So I need to put that there. There's my balanced chemical equation. So you could set up your BCCA table. Like, you can totally answer it this way, and then you would just kind of cross out the O2 column, because that's our excess, and so we know that the CH4 is the limiting. Or we can use a goalpost, a big long goalpost, where we are going from grams of methane to moles of methane to moles of water to grams of water. Now, grams to moles, so tells me my units as well, which is really nice. So I'm going to put these units up above. So grams of CH4 to moles of CH4 to moles of H2O to grams of H2O, and then I can put the units diagonally down below so that they will cancel. Grams of CH4, moles of CH4, moles of water. Okay, upper left is always what we're starting with. We're starting with 246.4 grams of methane. And now we have moles over grams or grams over moles, and that's going to come from my periodic table. So 1 carbon and 4 hydrogens. So I would add together 1 carbon, 12.01, plus 4 hydrogens, 1.008 times by 4. And that's how many grams per mole. So we get 16.042 grams per mole. Moles over moles comes from this balanced chemical equation. For every 1 mole of CH4, we get 2 moles of water. And then grams over moles goes back here, where we're going to add these together. So 2 hydrogens, 1.008 times by 2, plus oxygen, which is 16 grams per mole. 16 grams per mole. And we get 18.016 grams per mole. And we've worked with goalposts before. We know that this unit cancels when it's above and below, and we are left with grams of H2O. This is the top of the fraction, this is the bottom of the fraction, and I multiply it all together. So my top of my fraction, 246.4 times by 1 times by 2 times by the 18.06, close that parentheses, that's what's on the top, divided by, now the bottom of the fraction is the 16 times by 1 times by 1, close that up. So our final answer without sig figs, 553.44 grams of water. Now, what am I starting with? 1, 2, 3, 4 significant figures. So 1, 2, 3, 4 significant figures. That's what I'm going to end with. Alrighty, everyone. I think those are 2 good starting examples for us. We're going to be doing a lot of practice questions over the next 2 class periods, and so make sure that you come prepared. You're going to need your periodic table, you're going to need your calculator, and your package. Okay, thank you so much for your hard work.